4 astronauts are about to travel farther from Earth than any human being has ever gone, 280,000 miles, past the point where every signal dies, past the point where no one can reach them. And between that moment and the moment they touch water again, there is a stretch of 48 hours that keeps NASA's engineers up at night. If you stay with us, we are going to take you into every single second of it. The blackouts, the heat, the cracks in the shield that almost ended this mission before it started, and the reason this flight changes everything we thought we knew about going to space. If you enjoy this journey, hit like and subscribe. We are about to leave Earth. Take a breath. The clock is already running. 53 years ago, the last human beings to leave Earth's orbit stepped onto the moon and came home. After that, no one went back. For over half a century, we stayed close. We built a space station 250 miles above our heads and called it enough. We told ourselves the moon could wait. It could not wait forever. This February, NASA is launching 4 astronauts on a mission called Artemis II. And for the first time in over 50 years, human beings are going to travel beyond the edge of everything we have grown comfortable with. They are not going to land on the moon. This flight is something different. Something, in many ways, more important. They are going to fly around it, all the way around it, past the side we have never seen with our own eyes, and then they are going to come home. That sounds simple. It is not simple at all. Every system aboard the spacecraft has to work. The air they breathe, the water they drink, the shield that keeps them alive when they slam back into Earth at 25,000 miles per hour. Every single piece of this mission is being tested for the first time with actual human beings inside. If something fails, there is no space station nearby. There is no quick return. They will be farther from home than any person has ever been. This is confirmed. This is real. And it is happening right now. But here is the thing that most people do not understand about this mission. Artemis II is not just about going to the moon. It is about proving that we can. It is about answering a question that has been hanging over humanity for decades. Can we actually leave? Can we go beyond the bubble of protection that Earth gives us and survive? Because if we can do it here, around the moon, then one day we can do it to Mars. And beyond that, the entire future of our species depends on getting this right. The spacecraft is called Orion. It is roughly the size of a large van. 4 people are going to live inside it for 10 days. They are going to eat, sleep, work, and pray inside it. And when they come back, they are going to punch into Earth's atmosphere at a speed that would turn most vehicles into ash in less than a second. NASA has been preparing for this for years. They launched an identical capsule in 2022 with no crew inside and flew it around the moon and back. It worked. Mostly, there were some things that went wrong on that flight, things that worried engineers, things that some former astronauts have spoken publicly about, things we are going to get into very soon. But first, you need to know who is actually climbing into that capsule. Because these are not just names on a list. These are 4 real people who have agreed to go somewhere that could kill them. And what comes next is even stranger than the mission itself. There is a room in Houston, Texas, where 4 people have been sitting in quarantine since late January. No visitors. Masks on when they leave. Phones, but carefully, they are not sick. They are healthy. They are in quarantine because NASA cannot afford to let them catch a cold before the most important flight in 50 years. Their names are Reid Wiseman, Victor Glover, Christina Koch, and Jeremy Hansen. Wiseman is the commander. He is a former Navy test pilot. He has already spent 165 days in space aboard the International Space Station. He knows what it feels like to float. He knows what it feels like to be far from Earth. But he has never been this far. No one alive has. Glover is the pilot. He is the first black astronaut to live on the space station for a long-duration mission, 6 months aboard. He knows the silence up there. He knows the way Earth looks when you have been staring at it long enough that it starts to feel like a painting rather than a home. On Artemis II, he is going to see something no black astronaut has ever seen, the far side of the moon. Koch is a mission specialist. She holds the record for the longest single spaceflight ever completed by a woman, 347 days in a row aboard the station. She trained for years for this specific mission. She is the first woman who will ever travel to the moon. And then there is Hansen. He is Canadian. He flies for the Canadian Space Agency, and he is the first person from outside the United States who will ever leave low Earth orbit. That is confirmed. That is history, happening in real time. These 4 people have trained together since mid-2023. They have run simulations of every possible failure: engine out, life support malfunction, heat shield failure, communication loss. They have practiced making decisions with no one on the other end of the line to help them. Because out there, when something goes wrong, the signal takes over a second to reach Earth, and in certain parts of this mission, there will be no signal at all. They named their spacecraft. They called it integrity. That word matters. It is not just a name, it is a promise. Inside Orion, there is almost no room. 4 people sharing a space smaller than most people's kitchens for 10 days straight. The psychological pressure alone would break most humans. NASA has studied this. They have run experiments on isolation, on confinement, on what happens to the human mind when the nearest other person on Earth is 250,000 miles away. The results are sobering. But these 4 have been selected because they are built differently. They trust each other. They trust the machine around them. They are going to need both of those things very soon, because what this spacecraft has to do to get them home is something that has already gone wrong once before, and the details of that failure are about to change how you think about flying in space forever. Nothing on Earth shakes the ground quite like this. The Space Launch System is 322 feet tall. That is taller than the Statue of Liberty. It is wider than a city bus. And when it ignites, it produces 8.8 million pounds of thrust. That is 15% more raw power than the Saturn V rocket that carried the Apollo crews to the moon over 50 years ago. Picture that for a second. This machine is bigger than anything that ever carried humans to space before it. It works in layers. At the core, there are 4 engines. These are not new engines. They are refurbished from the Space Shuttle program. Each one has flown before. Each one has been rebuilt, tested, and certified to fly again. They burn liquid hydrogen and liquid oxygen together, and they produce an amount of heat and force that is almost impossible to picture without feeling it in your chest. Flanking the core on either side are 2 solid rocket boosters. These are the workhorses. They provide 75% of the total thrust at liftoff. They burn for about 2 minutes. 2 minutes. In that time, they push the entire stack high enough and fast enough that the rest of the job becomes possible. Then they separate. They fall away into the ocean. They are done. The core stage keeps burning, 8 minutes total. By the end of those 8 minutes, Orion is moving fast enough to stay in orbit around Earth. Then the core stage separates too. It falls away and burns up in the atmosphere. What is left is the upper stage, a smaller engine called the interim cryogenic propulsion stage, and the Orion capsule sitting on top of it. This is the moment everything gets quiet. The roaring stops, the shaking stops, and 4 astronauts open their eyes inside a capsule that is now floating in silence 250 miles above the ground. This is confirmed engineering. Every piece of it has been tested on the ground hundreds of times. But here is what keeps engineers honest. The Space Launch System has only flown once before. Once. That was Artemis I, the uncrewed test flight in 2022. It worked, mostly. There were surprises on that flight. Surprises that took over 2 years to fully understand. The rocket itself is not the thing that worries NASA the most. It is what happens after the rocket does its job. because once Orion is in orbit and the engines are quiet, the real mission begins. The crew will spend time circling Earth, running checkouts, testing systems, making sure everything inside the capsule is working before they commit to the deeper journey. They will practice maneuvering Orion by hand. They will run through emergency procedures one more time, and then they will point toward the moon. But before they get there, the first real challenge they face is something invisible, something that has been waiting around Earth for billions of years. A wall of radiation that you cannot see, cannot feel, and cannot avoid. And the crew is about to fly straight through it. The moment the engines cut, everything changes. 1 second, you are being crushed into your seat by a force 3 times the weight of your own body. The next second, you weigh nothing. Your arms float up in front of you. The straps are the only thing keeping you in place. The roaring disappears, and for the first time in your life, the only sound is the hum of a machine that is keeping you alive. This is what the Artemis II crew will feel within the first 10 minutes of their flight. Orion lifts off from Kennedy Space Center in Florida. The solid boosters ignite first, and the ground shakes for miles in every direction. People watching from the beaches nearby will feel it in their ribs. Then the core engines join in, and the entire structure begins to climb. Slowly at first, then faster. Then so fast that within minutes, the blue sky outside the windows starts to darken, and then it goes black. Space does not look like the movies. There is no dramatic pan across a starfield. There is just darkness, enormous, silent, endless darkness. And Earth shrinking behind you, glowing white and blue like something precious that someone left a light on inside of. The crew will spend roughly the first 2 days in orbit around Earth. This is confirmed by NASA. It is not wasted time. Every hour of it is packed with critical work. They are checking the life support system. They are making sure the oxygen is flowing. They are testing the displays, the controls, the communication links back to mission control in Houston. They are making sure that Orion, their home for the next 10 days, actually works before they take it somewhere it cannot come back from easily. There is a moment during these early orbits where the crew removes their spacesuits. They take off the orange flight suits they wore during launch. They put on regular clothes. This is deliberate. NASA wants to know how the life support system performs when human beings are actually living inside the capsule, breathing, moving, generating heat, exhaling carbon dioxide. The suits are backup. The capsule itself is the primary system. If the capsule fails at keeping the air clean, it does not matter how good the suits are, not for 10 straight days. During this time, the crew also practices something called proximity operations. They separate Orion from the spent upper stage of the rocket, then fly back toward it manually. They use cameras and their own eyes through the windows to line up with it, approach it, and pull away. This is practice for a future mission where they will need to dock with a lunar landing ship in orbit around the moon. It feels routine. It is not routine. Every single maneuver is a data point. Every single system reading is being recorded and analyzed by hundreds of engineers on the ground. And soon, one of those engineers is going to give an order that changes everything. The order to leave Earth's gravity behind. What happens next is a burn that no human being has attempted in over 50 years. Wrapped around Earth, invisible and deadly, there are 2 giant rings of trapped radiation. They are called the Van Allen belts. They stretch thousands of miles above the atmosphere in 2 layers, like enormous donuts of energy surrounding our planet. The inner belt is closer to Earth. The outer belt sits farther out, and both of them are filled with particles moving at tremendous speeds, particles that can damage living tissue if a human body is exposed to them for too long. This is confirmed science, discovered in 1958, studied ever since. So here is the question everyone asks: how did the Apollo astronauts survive flying through them? The answer is deceptively simple: they went fast. The Apollo crews blasted through the thinner edges of the belts in just a few hours, in and out. The exposure time was short enough that the radiation dose they received was roughly comparable to a medical scan done in a hospital. Uncomfortable knowledge, but survivable. Artemis II will do the same thing. The crew will pass through the belts on the way out to the moon, and again on the way back. Both times, they will be moving quickly enough that the total time spent inside the belts is measured in hours, not days. But speed is not the only factor. Direction matters too. The belts are not uniform. They are thicker in some places and thinner in others. NASA plans the trajectory carefully to send Orion through the weakest regions. This is confirmed. The path has been calculated and recalculated dozens of times. Inside Orion, there are 6 radiation sensors built into the walls at different locations. Each one is measuring the environment constantly. The crew members will also each carry a personal dosimeter in their pocket, a small device that tracks how much radiation they are absorbing in real time. If a solar storm suddenly increases radiation levels, these sensors will warn mission control immediately. And if that warning comes, the crew has a plan. They move to a specific area inside the capsule where the shielding is thickest. They stay there until the danger passes. This shelter inside Orion has been designed and tested specifically for this purpose. It is small, it is cramped, but it could save their lives if our star decides to throw something dangerous their way at the wrong moment. Here is what makes this more than just a checkbox on a mission list. The radiation data collected during Artemis II will be the most detailed ever gathered by a human-rated spacecraft beyond low Earth orbit. Every measurement the crew takes, every reading from every sensor, feeds directly into our understanding of how to keep people alive on longer trips. Trips to Mars, trips that could last months or even years. If we do not solve radiation protection, we cannot go further. The belts are just the beginning. Once the crew clears them, the deeper they go, the less Earth's magnetic field is there to shield them. But right now, clearing the belts is not the crew's biggest concern. That comes next. A single engine burn that will commit them to a journey from which there is no casual return. There is a moment on this mission where everything becomes irreversible. It does not look dramatic. There is no explosion, no giant flash of light visible from the windows. It is a controlled burn by the service module engine, a steady, precise push that lasts for a set amount of time. Engineers call it the trans-lunar injection burn. The crew will simply feel a gentle press back into their seats. And when it stops, they will be on a path toward the moon, a path that gravity alone will carry them along. This burn is the point of no return in a very real sense. Before it fires, Orion is still circling Earth, still close, still within reach of a relatively quick return if something goes wrong. After it fires, the crew is committed. They are leaving the neighborhood. They are heading into deep space, and the only way back is to complete the mission or rely on a safety system that we will talk about later, one borrowed directly from one of the most famous emergencies in the history of spaceflight. The burn itself is timed down to fractions of a second, too short, and Orion does not reach the moon. Too long, and it overshoots and drifts off into a trajectory that leads nowhere safe. This is confirmed. The calculations behind this single event involved thousands of hours of simulation and modeling by teams of engineers working across multiple time zones. After the burn, the engine goes quiet again, and the crew enters a stretch of about 4 days where they are simply traveling, moving outward, getting farther from Earth with every passing hour. During this leg, the crew monitors the spacecraft systems. They run experiments. They gather data on how their own bodies are responding to the environment. They eat. They sleep, though sleep in microgravity is its own strange experience, and we will get into that shortly. The spacecraft will also perform small correction burns along the way. These are tiny adjustments, nudges to keep Orion on exactly the right path. Think of it like steering a ship across an ocean. You do not just set a course and forget about it. You make small corrections constantly to account for currents and wind. In space, the currents are gravitational. The wind is the pull of Earth, the Moon, and even our star, all tugging on Orion at the same time. Each correction burn is planned in advance and executed with precision. Mission Control watches every one of them from the ground. And as the crew travels farther, something else begins to happen. The signal connecting them to Earth gets weaker. The delay gets longer. It takes over a second for a message to travel from Orion to Houston and back. That does not sound like much. But when you are making critical decisions, every fraction of a second counts. Soon, that signal is going to disappear entirely. And when it does, 4 human beings are going to be more alone than anyone in history has ever been. What that silence actually feels like is something no one on Earth can truly prepare them for. Your body was built for one place, Earth. Every cell in you, every system that keeps you alive, evolved over millions of years on the surface of this planet. Gravity pulls you down. Your heart pumps blood upward against that pull. Your bones harden themselves to carry your weight. Your inner ear learns to read the world based on which direction is down. Take all of that away, and your body does not know what to do. Within hours of reaching orbit, the Artemis II crew will begin to feel it. Blood shifts upward toward the head. The sinuses swell. The face puffs. The legs feel lighter, almost hollow. The inner ear sends signals that contradict what the eyes are seeing, and the result is something called space motion sickness. It hits most astronauts within the first day or two. It can be brutal. Nausea, dizziness, disorientation. The kind of feeling that makes you question every decision you have ever made. This is confirmed. It has happened to astronauts on nearly every mission to the International Space Station. The Artemis II crew has trained for this. They have taken medication. They have practiced techniques to manage it. But no amount of training fully eliminates the experience. The human body is not designed to float. Over the course of 10 days, other changes begin. The muscles start to weaken, slowly, because they no longer have to fight gravity. The bones begin to lose density, measurably, within just days. The heart, which has been working against gravity its entire life, starts to relax. It pumps less efficiently. It does not have to work as hard. And that lazy heart is something that worries researchers, because on longer missions, the damage compounds. NASA is paying close attention to all of this on Artemis II. The crew is wearing monitoring devices before, during, and after the mission. They are providing saliva samples at regular intervals to track how their immune systems are responding to the stress of deep space. Scientists want to know whether dormant viruses inside the astronauts' bodies reactivate in this environment. This has been observed before on the space station. Viruses like chickenpox and shingles waking back up in crew members who had been vaccinated as children. The crew is also carrying something called organ-on-a-chip technology. These are tiny devices, each one designed to mimic how a specific human organ behaves. They are being flown beyond Earth's magnetic protection for the first time ever. The data they produce will show how radiation and microgravity affect organs at a level never measured before. This is not just about keeping these 4 people healthy. This is about every human being takes a little over a second to make the round trip at lunar distance. 1 second does not sound like much, but it means the crew cannot have a normal conversation with the people on the ground. Every exchange has a pause built into it. A question, then silence, then an answer, then silence again. It is unnerving, it is isolating, and it is a constant reminder that help is not close. NASA is also testing something new on this mission, a laser communication system called O2O. Instead of using radio waves, it uses beams of infrared light to send data. Light moves at the same speed as radio signals, so the delay does not change, but the bandwidth is enormously greater. That means the crew could potentially send live, high-resolution video back to Earth. Images sharper than anything that has come from this far away before. There is a catch. Laser communication requires a clear line of sight, a straight, unobstructed path between the spacecraft and the ground station. And during one critical part of this mission, that line of sight is going to be completely blocked. The crew is going to fly behind the moon. When they do, the moon itself will sit between Orion and every antenna on Earth. Radio signals cannot bend around it. Laser signals cannot bend around it. Nothing can. For approximately 41 minutes, the crew will be in total silence. No signal in, no signal out. They will be completely cut off from mission control, from Earth, from every other human being alive. 41 minutes might not sound like long, but when you are farther from home than anyone has ever been, 41 minutes of absolute silence is something else entirely. And what happens during that silence is where this story really begins to get strange. The signal drops. One moment, mission control in Houston is there. Voices, data, a lifeline stretching across 280,000 miles of empty space. The next moment, there is nothing. The moon has moved between Orion and Earth, and it has swallowed every signal whole. This is planned. NASA knows it is coming. The crew knows it is coming. They have rehearsed for it. But knowing something is going to happen and actually experiencing it are two very different things. For 41 minutes, 4 human beings are the most isolated people who have ever lived. No one on Earth can hear them. They cannot hear anyone on Earth. If something goes wrong during this window, they cannot call for help. They cannot ask for guidance. They cannot even send a simple message saying they are alive. They are, for that stretch of time, completely and utterly alone in the universe. This is confirmed. It is a planned loss of signal, the same kind of blackout that happened during the Apollo missions when those crews swung around the far side of the moon. The physics has not changed. The moon blocks the signal. There is no way around it with current technology. NASA is already working on a solution for future missions. Relay satellites, small spacecraft placed in orbit around the moon that could bounce signals around the blockage. But those satellites do not exist yet. Not for Artemis II. On this flight, the silence is total. Inside the capsule during those 41 minutes, the crew has nothing to do except keep flying and keep each other company. The systems aboard Orion are designed to operate without ground support for exactly this kind of situation. The autopilot holds the trajectory. The life support keeps running. The crew monitors their instruments and waits. But here is what makes this moment more than just a technical inconvenience. This is the first time in over 50 years that human beings have been in this position. The last people to experience this kind of silence were the Apollo crews, and even they were not this far from Earth when it happened. The psychological weight of that silence is something NASA has studied carefully. Isolation research, conducted in places like Antarctica and in deep cave simulations, has shown that humans react badly to being cut off from the outside world. Stress hormones rise, sleep patterns change, decision-making becomes clouded. The crew has been trained to manage these effects. They have practiced staying calm and focused when the thread goes dark. But training and reality are separated by a gap that no simulation can fully bridge. When the 41 minutes end, the deep space network will reacquire Orion's signal and the connection will snap back into place. Mission control will hear from the crew again. Data will start flowing. The thread will be whole. And by that point, the crew will have seen something that only a handful of human beings in all of history have ever witnessed with their own eyes. The side of the moon that faces away from us forever. What it actually looks like up close is going to take your breath away. Most people have never seen it, and for most of human history, no one could. The moon is tidally locked to Earth. That means it rotates at exactly the same rate that it orbits us. The result is that the same side always faces us. Every photograph you have ever seen of the moon, every painting, every drawing, every time you looked up at the night sky and saw that familiar face, you were seeing the same half, always the same half. The other side exists. It has always existed, but for centuries, it was a complete mystery. The first spacecraft to photograph it was a Soviet probe in 1959, and what it revealed shocked scientists. The far side looks nothing like the near side. The near side, the one we see, is relatively smooth in large areas, covered by dark patches of hardened lava called meria. The far side is cratered, densely, violently cratered, covered in impact scars from billions of years of collisions with space debris. It looks like something that has been hammered without mercy. This is confirmed. Decades of robotic exploration have mapped the far side in extraordinary detail. The Artemis II crew is going to see it with their own eyes. Orion will fly around the Moon at a closest approach of roughly 4,000 miles above the far side surface. That is high enough to be safe, close enough to see. Through the windows of the capsule, the crew will look down at a landscape that no human being saw with their own eyes until Apollo 8 in 1968. And even those astronauts only caught a glimpse, a brief visual moment as they swung past. Artemis II goes farther around. The crew will have time to observe, to photograph, to take in the scale of what they are seeing. A world made entirely of craters and ridges and ancient stone, stretching to every horizon, with nothing moving, nothing growing, nothing breathing. The silence outside is absolute. There is no atmosphere on the Moon, no wind, no sound at all. The crew cannot hear it, obviously, but knowing that fact while looking at that landscape creates something that astronauts have described in ways that are difficult to put into words. A feeling of being very small, a feeling of looking at something that does not care whether you are there or not. NASA has the crew trained in lunar observation and photography. They have studied crater shapes, surface textures, and color variations during training sessions back on Earth. Every image they capture from this vantage point will be used by scientists studying the Moon's geology, its history, and the resources that might one day make it a place where people live and work. But the view is not the reason this moment matters most to the mission. The reason is what happens immediately after, because once the crew has passed the closest point to the Moon's own gravity begins to do something extraordinary. It grabs Orion, it pulls on it, and it starts to throw it back toward Earth without a single engine firing. That is the gravity slingshot, and it is one of the most elegant and dangerous tricks in all of spaceflight. The Moon does not just sit there. It is moving. It has always been moving. Right now, it is traveling around Earth at roughly 2,000 miles per hour, and when a spacecraft flies close enough to it, that motion does something extraordinary. It reaches out with gravity and pulls the spacecraft along, like a hand grabbing hold of something flying past and flicking it in a new direction. This is the gravity slingshot, and on Artemis II, it is the mechanism that sends the crew home. No engine fires for this. That is the part that surprises most people. Orion does not ignite anything to begin its return trip. The Moon does the work. Its gravitational pull bends Orion's path, curves it around, and redirects it back toward Earth. The crew gains speed in the process, speed borrowed directly from the Moon's own orbital motion. This is confirmed physics. It is not a theory or an experimental technique. It has been used by space agencies for decades. The Voyager probes, the ones that are now drifting beyond the edge of our solar system, used gravitational assists from Jupiter and Saturn to reach their incredible speeds. The principle is identical. Think of it like a ball rolling past a spinning wheel. If the ball gets close enough, the wheel grabs it and flings it away faster than it was moving before. The wheel loses a tiny, imperceptible amount of its own energy in the process, but the ball gains a great deal. On a cosmic scale, the Moon loses almost nothing. Orion gains everything it needs. The precision required to make this work is extraordinary. NASA calculated the exact trajectory Orion must follow as it swings around the Moon. The angle of approach, the distance, the speed. All of it had to be exactly right. A fraction of a degree off, and the slingshot does not work as designed. Orion could end up moving in the wrong direction, or not moving fast enough to reach Earth on the planned timeline. This is why the correction burns fired during the outbound trip mattered so much. Every small adjustment on the way to the moon was being made, in part, to set up this moment. The slingshot is the payoff of days of careful navigation. After the slingshot, Orion is on a new path, heading home, moving fast, and now the clock starts running on the most dangerous stretch of the entire mission. Because the crew is not just traveling back to Earth, they are traveling back to Earth at a speed that will demand everything from this spacecraft. Everything from the shield, everything from the systems, everything from the crew. The return leg takes about 4 days. During that time, the crew monitors and adjusts. They run final checks on every system. They prepare for what is ahead. And what is ahead is a question that no amount of preparation can fully answer, because out here, 280,000 miles from the nearest human being, if something goes wrong, there is no one coming to fix it. That fact, and what it really means for 4 people inside a capsule, is the next thing you need to understand. If something goes wrong out there, no one is coming to get them, not in an hour, not in a day, not at all. There is no spacecraft in existence that could reach Orion at lunar distance in time to make a difference. There is no emergency protocol that ends with a rescue ship pulling up alongside and transferring the crew to safety. There is nothing. This is the reality of deep space travel, and it changes everything about how you design a mission, how you train a crew, and how you think about risk. When astronauts fly to the International Space Station, rescue is close. The station orbits 250 miles above Earth. Emergency vehicles are docked to it at all times. If something fails, if there is a fire, if the station is struck by debris, there are plans to get people off and back to the ground. Those plans are not perfect. They are not guaranteed, but the option exists. The infrastructure is there. On Artemis II, that infrastructure does not exist. The moment the crew left Earth orbit and committed to the lunar trajectory, they stepped outside the reach of any rescue capability humanity has ever built. This is confirmed. There is no vehicle, no crew, no system anywhere in the solar system that could intercept Orion at the distances and speeds involved. This is why every system aboard the capsule was designed with redundancy. The life support has multiple independent pathways to keep the air clean. The navigation has layers of fallback. If one thing fails, another takes over. If that fails, another is waiting. But redundancy has a limit. It protects against individual failures. It does not protect against everything. A hull breach, severe enough to depressurize the capsule. A fire inside the crew compartment that overwhelms the suppression systems. A cascade failure where one broken system causes a chain reaction through connected systems. In scenarios like these, redundancy buys time. It does not change the outcome. NASA has studied these scenarios in excruciating detail. They have modeled failure cascades. They have run simulations where one system fails, then 2, then 3. They have built the crew's training around the idea that in a true emergency, the 4 people inside Orion are the last line of defense. There is no one else. No mission control operator can reach in and fix something. No engineer can physically touch the spacecraft. The crew has to diagnose, decide, and act, sometimes within seconds. This is part of why the mission was designed as a flyby and not a landing. Every hour spent in deep space is another hour where a catastrophic failure becomes statistically more likely. A flyby minimizes that exposure. It is the fastest possible path around the moon and back. Get close, do what you came to do, come home. The crew understood this when they signed up. They trained for it. They have accepted it in a way most people on Earth cannot fully grasp. But there is one piece of design that gives them a margin even the worst failures cannot entirely erase. A safety net built into the very shape of their flight path. And it was born from one of the most harrowing emergencies in the history of spaceflight. April 10th, 1970, an oxygen tank aboard Apollo 13 explodes 2 days into the mission. The blast tears through the service module. The main engine is gone. Power is failing. The astronauts have no way to land on the moon. They have almost no way to get home. Mission control in Houston is scrambling. Everyone in the room knows what is at stake. And then someone looks at the flight path. The trajectory Apollo 13 was already flying had a specific property built into it. If the crew did nothing else at all, if not a single engine fired again for the rest of the mission, the path they were on would carry them around the moon and back to Earth on their own. Gravity would do all the work. It was called a free return trajectory, and it saved 3 lives. Artemis II flies on one. This is confirmed. It is the single most important safety feature on the entire mission, and it exists because of what happened to Apollo 13 over 50 years ago. Here is how it works in plain terms. When Orion fires its burn to leave Earth orbit and head toward the moon, it does not just aim at the moon. It places itself on a precise curved path. That path is shaped by the gravitational pull of both Earth and the moon working together, and that shape has one critical property. It loops around the moon and comes back to Earth, all by itself, without any further engine input. Think of it like a river with a natural bend. If you put a boat in the current at the right spot, the current will carry it around the bend and back downstream on its own. You do not have to paddle. The shape of the river does the work. The free return trajectory is that current. Now, this does not mean the mission is without risk if the engines fail. The trajectory brings Orion back in the general direction of Earth, yes, but it brings it back at a specific speed and angle. If that angle is slightly wrong when Orion reaches the atmosphere, the reentry could be dangerously steep or dangerously shallow. Small correction burns along the way exist precisely to fine-tune that angle and keep everything inside survivable limits. But here is the power of this design. Even in a worst-case scenario where the engines stop working entirely, the crew still has a chance. They still come back in the neighborhood of Earth. They still have a path home. That is more than most spacecraft in history could say if their engines failed in deep space. NASA weighed this design against other trajectory options when planning Artemis II. Some alternatives would have been faster. NASA chose the free return path deliberately. The safety margin it provides outweighed every other consideration. The crew knows this. It is quietly built into their confidence. Somewhere beneath the checklists and the training and the calm professionalism, each of them understands that the shape of their flight path itself is working to bring them home. But the path only gets them close. What happens when they actually arrive is a completely different fight. And that fight starts within the next 48 hours. The 48 hours begin now. From this point in the mission, everything that remains is concentrated into a tight, unforgiving sequence. The crew is heading home. But getting home is not one event. It is a chain of events, each one depending on the last, each one carrying its own way to fail. And if any single link in that chain breaks, the ones after it do not happen. This is the window that keeps NASA engineers awake at night. The first segment is the return flight itself, roughly 4 days of travel back toward Earth. During this time, the spacecraft is still functioning, the crew is still working, and small correction burns are still being fired to keep Orion aimed at the right point in the atmosphere. This sounds routine. It is the most routine part of what remains. But routine does not mean safe. The spacecraft has been running for the better part of a week. Systems are cycling, wearing, accumulating stress in ways that were not present on day one. The crew is also under pressure that has been building since they left. Days of microgravity, days of confinement, days of knowing no one can reach them if something goes wrong. That kind of sustained stress does not show on instruments. It lives inside the people carrying it. After the return flight, the chain tightens. The service module has to separate cleanly. This is the section of the spacecraft that has carried the engines, the power, and part of the life support for the entire mission. It cannot come back with the crew. It would burn up in re-entry anyway, and its presence would change the shape and weight of the capsule in ways that would make safe landing impossible. So it detaches, and once it does, it is gone. The crew module is on its own. Then comes re-entry. The capsule hits the atmosphere at a speed that has never been attempted with people inside before. Not at this exact speed, not with this exact vehicle. The heat shield takes the force of it. The crew takes the G-forces. And somewhere in that sequence, something that went wrong on the last flight becomes either a solved problem or a repeating one. Then comes the fire. Thousands of degrees of superheated air wrapping around the capsule, minutes of it. A second communications blackout while the plasma blocks every signal. Then comes the parachutes, 11 of them, firing in sequence, slowing the capsule from hundreds of miles per hour to a survivable speed for splashdown. Each step is a gate. You pass through one, and the next one opens, but none of them open automatically. Each one requires the spacecraft to perform exactly as designed. Each one requires the crew to be sharp, aware, and ready to act if something deviates. The 48-hour window is not one big moment of danger. It is a dozen smaller moments, strung together with almost no margin between them. And the first of those moments, the one that has dominated every conversation NASA has had about this mission for over 2 years, involves a piece of material on the bottom of the capsule that already failed once. In late 2022, an unmanned capsule called Orion splashed down in the Pacific Ocean after flying around the moon and back. No crew inside, just instruments, sensors, and cameras recording everything. When engineers pulled it from the water and began their inspection, they found something that should not have been there. Over 100 spots on the heat shield where the protective material had cracked, broken apart, and detached from the surface. Chunks of it had come loose during re-entry and streamed behind the capsule like debris trailing a comet. The very material designed to keep the spacecraft from burning up had peeled away while the capsule was under maximum thermal stress. This is confirmed. NASA's own Office of Inspector General documented the damage. The language in their report was precise and direct. The anomalies, it stated, posed significant risk to crew safety. Now, here is the part that changes the conversation entirely. The heat shield on Artemis II is the same design, the same material, the same construction. NASA did not replace it. They did not rebuild it from scratch. They decided to keep what they had and change how the capsule flies through the atmosphere instead. That decision divided the space community. Some engineers and former astronauts spoke publicly about their concerns. They argued that flying a shield with a known failure history, even with a modified re-entry profile, was an unacceptable gamble with 4 lives. The criticism was sharp, it was specific, it was grounded in decades of experience. NASA pushed back. An independent review panel examined the issue over the course of months. They studied the failure data from Artemis I. They ran new ground tests. They modeled the modified re-entry dozens of times. Their conclusion was that the shield, flown on the new trajectory, could keep the crew safe. Could. That word carries weight. The shield itself is a disc roughly 16.5 feet across, fixed to the bottom of the crew capsule. It is the largest heat shield ever built for a human-rated spacecraft. Its entire purpose is to stand between the crew and temperatures that would destroy the capsule in seconds. Every piece of it was inspected before Artemis II was cleared to fly. Teams of engineers examined the surface under close magnification, looking for any sign of the same kind of damage found on the previous mission. They found the shield to be in acceptable condition. Acceptable. another word that carries weight. The shield has to survive 2 separate entries into the atmosphere on this flight. 2 chances for the same kind of failure to happen again. 2 chances for cracks to open, for material to break loose, for the thermal protection to compromise itself at the worst possible moment. NASA is confident. The data supports their decision. The review panel endorsed it. The crew has accepted it. But confidence is not certainty. And the reason those cracks appeared in the first place, the actual mechanism that caused them, is a story about physics and engineering that reveals just how close this mission came to being grounded entirely. What happened inside that material, and why, is the next piece of this puzzle. Avcoat is not a single substance. It is a mixture, a carefully engineered blend of resins and other compounds packed into thousands of tiny honeycomb cells embedded in the surface of the heat shield. Each cell is small, but there are hundreds of thousands of them, covering the entire underside of the capsule, like a tightly woven net of protective material. Here is what is supposed to happen when Orion hits the atmosphere at high speed. The air outside compresses and heats up. That heat strikes the avcoat. The material begins to char, burning in a controlled, layered way. As it chars, it carries heat energy away from the capsule. The charred layer sits on the surface like armor, absorbing blow after blow of thermal stress while the layers beneath it keep doing the same job. Think of holding your hand over a candle flame with a thick glove on. The glove chars, it darkens, but it stays in place, and your hand stays safe underneath. That is the design. That is how avcoat is supposed to behave. And for the most part, across decades of use on earlier spacecraft, it has. So what went wrong on Artemis I? The answer comes down to gas. When avcoat chars, it produces gas as a byproduct. Under normal conditions, that gas vents outward through the material, escaping into the atmosphere around the capsule. It is supposed to leave. That is part of the design. But during the Artemis I re-entry, something disrupted that process. The capsule did not come straight down. It used a technique where it dipped into the atmosphere, began to slow, and then lifted back out into space briefly before dropping back in for the final descent. During that lifting phase, the heating rate dropped. The outside of the shield cooled slightly, and the gas did not vent. It got trapped inside the avcoat, underneath the charred layer, building pressure. The gas expanded. It pushed outward against the material above it, and the charred crust cracked open. Chunks broke free and streamed behind the capsule into the atmosphere. This is confirmed. NASA spent over 2 years investigating before releasing their findings. The root cause was not a manufacturing defect. It was not a flaw in the material itself. It was the specific sequence of heating and cooling that happened during that re-entry profile, a sequence that the ground-based testing at the time could not fully replicate. That gap between what you can test on the ground and what actually happens in flight is one of the most uncomfortable truths in aerospace engineering. You can model, you can simulate, you can run tests in controlled environments, but the real atmosphere, at real speeds, with real heat, behaves in ways that no laboratory can perfectly reproduce. NASA has since built better testing capability. They have run the avcoat through conditions that more closely match what Artemis II will face. The results have supported their decision to fly. But the fundamental tension remains. The material has shown it can fail under certain thermal conditions. The new re-entry profile is designed to avoid those conditions. Whether it succeeds at that is something only the flight can prove. And that proof is coming in the next chapter. Orion is not going to come straight down into the atmosphere. It is going to dip into it, slow down, lift back out, and then come in again. 2 entries, 2 separate encounters with the wall of air that stands between deep space and the surface of Earth. And the reason NASA designed it this way has everything to do with the speed at which the crew is arriving home. Returning from the moon is a fundamentally different problem from returning from the space station. Spacecraft coming back from low orbit are moving at roughly 17,500 miles per hour. Fast, by any standard, but manageable. Decades of flights have proved that. The atmosphere absorbs the energy. The heat shield takes the heat. The capsule slows down and lands. Coming back from lunar distance, Orion is moving at 25,000 miles per hour, 40% faster. And if it tried to come straight in at that speed, the forces would be brutal. The deceleration would crush the crew. The heat would be sustained and extreme. The shield would be under thermal stress for far too long in a single continuous burn. So NASA split the problem. The first entry begins at the edge of the upper atmosphere. Orion dips in at a shallow angle. The air begins to push back. The capsule slows. Heat builds on the shield. But before the full weight of the atmosphere can lock in, Orion uses its shape and its angle of attack to generate lift. It rises back up. It exits the atmosphere briefly. In that gap between the two entries, the speed has dropped. Some of the heat has been dealt with. The shield has absorbed one round of punishment and survived it. Then the second entry begins. This time, the speed is lower. The forces are more moderate. The remaining deceleration happens in a way that the spacecraft and the crew can survive. Two manageable challenges instead of one impossible one. That is the logic. This technique was tested on the uncrewed Artemis I flight. It worked as designed. The capsule skipped as planned, landed precisely where it was supposed to, and the skip re-entry itself performed well. But it was also during that skip, specifically during the brief lifted phase between the two entries, that the gas trapped inside the avcoat and caused the shield to crack. NASA has responded by shortening that lifted phase on Artemis II. The time the capsule spends between entries is being reduced. The heating stays more consistent. The gas has less opportunity to build pressure. The temperature drop that caused the problem last time is supposed to be smaller this time. Supposed to be. Those words carry everything. The skip also gives NASA something the Apollo missions did not have: precision landing. The two-entry technique allows engineers to calculate and control exactly where in the ocean Orion touches down. Recovery crews will be waiting within miles of the splashdown point, the Pacific Ocean off the coast of California. But precision landing only matters if the shield holds through both entries. And holding through both is the test that no ground simulation can fully guarantee: 25,000 miles per hour. Say that number out loud and let it land. In one single hour, at that speed, you would travel from one side of the United States to the other and back again, twice, and Orion is going to slam into a wall of air, moving at exactly that pace. This is the fastest re-entry speed ever attempted by a spacecraft carrying human beings. Confirmed. Apollo capsules reached similar speeds coming back from the Moon, but those were smaller and lighter vehicles with different thermal profiles. Orion is larger, it is heavier, and the shield protecting it has already shown it can break under comparable conditions. To understand what 25,000 miles per hour means in real terms, think about what else moves that fast. A rifle bullet travels at roughly 2,000 miles per hour. Orion is moving 12 times faster than that. A meteorite entering Earth's atmosphere can reach speeds in that range, and most of them burn up entirely before they reach the ground. They do not survive the entry, they are destroyed by it. Orion has to survive it. The moment the capsule touches the upper edge of the atmosphere, the air in front of it begins to compress. Compressed air heats up fast. Within seconds, the temperature outside the capsule is climbing into the thousands of degrees. The air is not just hot, it is transforming. The molecules are being torn apart by the force and the heat, stripped of electrons, turning into a state of matter called plasma. Plasma glows. It wraps around the capsule in a shell of light. From the ground, if you could see it at that altitude, Orion would look like a bright streak burning across the sky, a star falling. Inside the capsule, the crew does not see any of that. Their view through the windows is pointed inward during re-entry, away from the heat. What they see are instruments, altitude, speed, temperature readings from sensors mounted on the outside of the shield, numbers that tell them whether the material beneath them is holding or beginning to give. The deceleration hits them physically. After days of floating in weightlessness, their bodies suddenly feel heavy again. During the first entry, the G-forces will reach roughly 4 times normal gravity. That means each crew member feels 4 times their own weight pressing them into their seat. It is uncomfortable. It is disorienting. Their muscles, weakened by days without gravity, have to work again without warning. But it is survivable. Fighter pilots experience similar forces. The crew has trained for it extensively. What cannot be trained for perfectly is the uncertainty. The atmosphere is not perfectly uniform. It has pockets of higher density and lower density, thermal currents, variations that even the best models cannot predict with complete accuracy. Every re-entry, no matter how well planned, carries a small margin of the unknown. That unknown is what the shield has to absorb. And underneath that shield, the material is about to face something that dwarfs anything it has experienced on the ground. The fire is next, 5,000 degrees Fahrenheit. That is the temperature the outside of Orion's heat shield will reach during re-entry. 5,000 degrees. Steel melts at roughly 2,700. Iron melts at around 2,800. The structural frame underneath the shield, the skeleton that holds the capsule together, would begin to fail long before the air around it climbed to 5,000. The shield is the only thing standing between the crew and that temperature. 5,000 degrees is roughly half as hot as the visible surface of our star. And for several minutes, the 4 people inside Orion are going to be flying through an environment that hot, separated from it by a single layer of material that already cracked the last time it was tested at these temperatures. The fire is not even. It pulses. It surges. The atmosphere is not a uniform wall. It shifts and varies as the capsule descends and the heat output fluctuates with it. The shield has to handle every variation, every surge, every moment where the thermal load spikes beyond what the engineers modeled. During the most intense phase of the fire, something else happens. The plasma surrounding the capsule, that superheated shell of ionized air, becomes thick enough to block radio signals. The crew loses contact with mission control, a second blackout, shorter than the one behind the moon, but it happens at the exact moment when everything aboard the spacecraft is under maximum stress. No one on Earth can hear them. They cannot hear Earth. The instruments are the only voices in the room. This is confirmed. It has happened on every high-speed re-entry in history. The physics does not bend for human schedules. Inside the capsule, the crew watches their displays. Temperature readings from sensors on the outer surface of the shield tick upward in real time. They can see the numbers climbing. They can see how close the material is to its limits. And they know, because they have studied the data from Artemis I, that limits have been exceeded before. The memory of Columbia sits underneath all of this. In February of 2003, the Space Shuttle Columbia broke apart during re-entry because a piece of foam had damaged its thermal protection during launch. The damage was small. It was not detected before the crew attempted to come home. When Columbia hit the atmosphere, the compromised shield could not do its job. The vehicle and the 7 people inside it were destroyed. NASA investigated that accident for months. The findings changed how the agency thought about thermal protection, about inspection, about the consequences of assuming a system will perform because it performed last time. Those lessons are embedded in every decision made about Artemis II's shield. The fire lasts minutes, dense, violent, relentless minutes, and then, gradually, the capsule has slowed enough that the plasma begins to thin. The glow fades. The temperature starts to drop. The radio signal returns. Mission Control hears from the crew again. The worst of the heat is over. But the crew is still not home. There is still one final sequence of events that has to work perfectly before 4 people touch water, and it begins with a separation that cannot be undone. While the crew is making its way home, another threat is running on its own schedule entirely. It has nothing to do with the moon. It has nothing to do with the speed of re-entry or the heat shield. It comes from a completely different direction, and it can strike at any point during the mission, without warning, without pattern, and without mercy. It comes from our star. The star that lights and warms this planet is not the calm, steady presence most people picture. It is a churning, violent sphere of superheated gas that erupts constantly, solar flares, coronal mass ejections, bursts of charged particles launched outward at millions of miles per hour, blasting through space in all directions. Most of the time, Earth's magnetic field catches those particles and deflects them. They wrap around the planet and never reach the surface. We are shielded by a force field we cannot see, one that has protected life here for billions of years. Orion is leaving that force field behind. Beyond a certain distance from Earth, the magnetic protection thins and eventually disappears. The crew on Artemis II is traveling well beyond that boundary. Out there, if our star decides to erupt while they are exposed, the radiation from that eruption hits them directly. There is no planetary shield. There is nothing between the crew and the particle storm except the walls of the capsule itself. This is confirmed. Solar activity is monitored constantly by ground-based observatories and by spacecraft stationed between Earth and our star. NASA tracks solar weather the same way a meteorologist tracks storms on Earth. And just like storms on Earth, solar events cannot be predicted perfectly more than a few days out. Inside Orion, there is a specific area where the shielding is thickest. It is a small section of the capsule, cramped and tight, where the walls are lined with extra layers of material designed to absorb and block incoming radiation. This is the shelter. If a solar storm warning comes in while the crew is on the way to or from the moon, Mission Control sends the alert. The crew moves to the shelter. They stay there until the storm has passed. They wait. They monitor. They breathe in a space barely large enough for 4 people to sit close together. NASA tested the shelter's effectiveness during Artemis I. Sensors throughout the capsule recorded radiation levels during the entire flight. The data showed that the shelter performed as designed. Moving to it during a particle event would meaningfully reduce crew exposure. The crew has drilled this procedure dozens of times. They know exactly where to go. They know how to seal themselves in. They know how long typical solar events last. But here is the uncomfortable truth underneath all of it. A solar storm can happen at any time. It does not wait for convenient moments. It does not care about mission timelines. If one hits while the crew is in the middle of a critical maneuver, they have to stop what they are doing and go hide. The star that gave us life can also end it. Out there, that tension is very real. Every breath you have ever taken has been free. You have never had to think about it. You open your mouth, air comes in, it fills your lungs, you exhale, the atmosphere does the rest. It is the most automatic thing a human body does, and for every person who has ever lived on Earth, it has never, not once, required a machine to make it happen. On Artemis II, that changes. Inside Orion, the air the crew breathes is not coming from outside. There is no outside. There is nothing outside except the vacuum of space, a void where a single breath would kill you in seconds. Every molecule of oxygen the crew pulls into their lungs has to be manufactured by a system aboard the capsule, and every molecule of carbon dioxide they breathe out has to be captured and removed before it builds up to a level that poisons them. This system is called the Environmental Control and Life Support System. It is the least glamorous piece of technology on the entire mission. It is also, in many ways, the most critical. Here is how it works. The system takes water and splits it apart using electricity. Water is made of hydrogen and oxygen. When you run an electrical current through it, the two separate. The oxygen goes to the crew. The hydrogen gets stored or used elsewhere. This process is called electrolysis, and it has been used on spacecraft for decades. It is confirmed technology. It works. The carbon dioxide side is harder. Every time a crew member exhales, carbon dioxide enters the air inside the capsule. Carbon dioxide is not immediately deadly, but it accumulates. And if the concentration rises above a certain level, it begins to cause headaches, confusion, nausea, and eventually unconsciousness. The system constantly pulls air through a filter material that chemically binds to the carbon dioxide and removes it from the atmosphere inside the capsule. Water recycling is the third piece. The crew produces water as waste, sweat, exhaled moisture. The system collects all of it, filters it, and turns it back into drinking water. The crew on Artemis II will be drinking water their own bodies produced, recycled, purified, drinkable. That fact takes a moment to sit with. The entire system runs continuously for 10 days straight. It does not sleep, it does not take breaks, and if it stops working, the clock starts immediately. Without fresh oxygen and without carbon dioxide removal, the air inside the capsule becomes unbreathable in a matter of hours. There is no way to open a window. There is no way to step outside for fresh air. The system has to keep running on its own, with what it has, for the duration of the mission. NASA tested components of this system extensively on the ground before the flight. Some of those tests revealed problems that caused delays to the mission timeline. The issues were fixed, the system was recertified, but the real test, the only test that truly counts, is 10 days of continuous operation with 4 living, breathing human beings depending on it. If the air fails, nothing else on the mission matters. The parachutes, the shield, the trajectory, all of it becomes irrelevant. The crew needs to breathe first. Everything else comes after. Before re-entry begins, something has to be destroyed, not destroyed carelessly, destroyed deliberately. Cut away with precision, at exactly the right moment, using explosive bolts that fire on command and sever the connection between 2 halves of a spacecraft in a fraction of a second. One half goes on to carry 4 people back to Earth. The other half burns up alone in the atmosphere, and no one will ever see it again. This is the service module separation, and it is one of the most consequential moments in the entire mission. The service module is the section of Orion that has been doing the heavy lifting since the moment the crew left Earth orbit. It carried the main engine, it carried the power, it carried part of the life support. For 10 days, it has been the beating heart of the spacecraft, the section that made everything else possible. And it cannot come home with them. The reason is physics. When Orion hits the atmosphere, its shape and its weight determine how it moves through the air. The service module, attached to the back, would change that shape in ways that would make a safe re-entry impossible. It would also burn up anyway. The temperatures during re-entry would vaporize it regardless. So NASA cuts it away before the fire starts, while the spacecraft is still in the cold and the quiet of space. The separation happens through a ring of small explosive charges called pyrotechnic bolts. They are built into the connection point between the 2 halves. When Mission Control sends the command, the bolts fire simultaneously. The connection breaks. The 2 halves drift apart. It takes less than a second. After the cut, the crew module is alone. No engine behind it. No power source other than its own internal batteries. No backup. The capsule that will carry them through re-entry and down to the ocean is now exactly what it is: a sealed shell, a heat shield on the bottom, parachutes packed inside for later, and 4 people inside it with nothing between them and the atmosphere except engineering and hope. This moment carries weight that goes beyond the technical. The service module has been their companion for the entire journey. It has kept the air clean. It has powered their instruments. It has fired the engines that steered them through deep space. Cutting it away is, in a sense, cutting away the last piece of infrastructure that connected them to the machinery of exploration. After the cut, they are passengers. The capsule is going to do what it does. The atmosphere is going to do what it does, and the crew is going to sit inside and trust that the engineering holds. NASA has tested service module separation many times, on both robotic and crewed missions going back decades. The pyrotechnic bolts are reliable. The procedure is well understood. This is confirmed. But reliable does not mean guaranteed. The fire is already waiting. And between the fire and the ocean, there are 11 pieces of fabric that have to open in exactly the right order. The fire is over. The capsule has survived re-entry. The speed has dropped from 25,000 miles per hour to something far more manageable. And now, for the first time on this mission, the crew is falling. Not drifting, not floating, falling toward the ocean, toward the ground, toward the end of everything they have been through for the past 10 days. And the only thing slowing them down is a system of parachutes that has to open in exactly the right sequence, at exactly the right time, or the impact will kill them. There are 11 parachutes aboard Orion. They do not all open at once. That would tear them apart. They fire in a carefully choreographed sequence, each stage reducing the speed before the next stage takes over. It begins with the pilot chutes. These are small. They are fast. They deploy first, and their job is simple. They pull the next set of chutes out of their packed compartments. Without the pilot chutes, nothing else opens. They are the trigger for the entire system. Next come the drogue chutes. These are larger, and they do real work. They catch the air and begin to slow the capsule down from hundreds of miles per hour. The deceleration is sharp. The crew feels it as a sudden jolt, a hard press back into their seats after the relative weightlessness of the descent. And then the main chutes deploy, 3 of them. Each one is roughly 100 feet across. They open in sequence, not all at once, to prevent the sudden shock from tearing the fabric. When all 3 are fully open, the capsule is descending at roughly 17 miles per hour, slow enough to survive, fast enough that hitting the water is still a serious impact. This is confirmed engineering. The parachute system was tested hundreds of times before the first crewed flight. Individual chutes were dropped from aircraft. The full sequence was run in computer models thousands of times. Every possible failure mode was identified, and a backup plan was built around it. And there are failure plans. If one of the 3 main chutes fails to open, the system can still land safely on 2. The margins were designed with that possibility in mind from the start. 2 chutes are enough. 1 is not. But 2 is survivable. The crew watches the deployment through their instruments. Altitude is dropping. Speed is dropping. The ocean is growing in their awareness, present in every number on every screen. They are close now. Closer than they have been to solid ground in 10 days. The final minutes are quiet by comparison to everything that came before. No fire, no plasma, no blackout. Just the steady pull of gravity and the sound of air moving past fabric above them. 3 enormous canopies doing the last job of the mission. And then the ocean comes up to meet them. The impact will be harder than most people expect. 17 miles per hour into water does not feel gentle, but the capsule was built for it. The crew was trained for it. And in the seconds after they touch down, the 48-hour window will finally close. But the mission is not over yet. Not quite. NASA has lost people before. Not in deep space. Not on the way to the moon. On the way out of Earth's atmosphere. And on the way back into it. Twice. And both times, the reason was the same. Someone inside the organization knew something was wrong. Someone raised the alarm, and that alarm was not loud enough to stop the launch. The first time was Challenger, January 28, 1986, a cold morning in Florida. The space shuttle was sitting on the launch pad, and engineers at the company that built one of its components had spent the night before trying to stop the flight. They had data. they had proof. The rubber seals inside the solid rocket boosters, called O-rings, were not designed to function properly in cold temperatures. The seals could fail. If they failed, hot gas would leak through the joint and burn through the external fuel tank. The engineers begged. Their managers overruled them. The launch went ahead. 73 seconds after liftoff, the O-ring failed. The hot gas burned through. The external tank ruptured. The shuttle broke apart. 7 people died. This is confirmed history. The Rogers Commission investigated for months. Their findings were devastating. The failure was not a surprise. It was a known risk. It was a risk that was dismissed because of pressure to fly on schedule. The second shuttle disaster, Columbia, was covered in an earlier chapter in this script. The pattern was identical, a known risk, a warning that was not heeded, an assumption that the system would work because it had worked before. 2 disasters, 14 people dead, and in both cases, the root cause was not just an engineering failure, it was a failure of the people and the systems around the engineering. NASA rebuilt after each one. After Challenger, the agency restructured how it made decisions about flight readiness. Engineers were given more authority to say no. The culture shifted, at least on paper, toward caution over schedule. After Columbia, the shift went deeper. NASA created new inspection protocols, new communication requirements, new ways for engineers at every level to raise concerns without fear that their voices would be ignored. Now look at the heat shield debate on Artemis II. Over 100 cracks found on the previous flight. Engineers and former astronauts raising alarms. NASA conducting a 2-year investigation before clearing the mission to fly. An independent review panel brought in to examine the data. That process, that level of scrutiny, did not exist in 1986. It did not exist in 2003. It exists now because of what happened on those 2 mornings, because 14 people paid the price for what happens when warnings are ignored. Whether the heat shield debate was resolved correctly is a question only the flight can answer. But the fact that it was a debate at all, that it took 2 years and an independent panel before NASA said yes, is itself a lesson learned, a change written in grief. The crew knows this history. Every engineer working on Artemis II knows it. The weight of Challenger and Columbia sits in every room where a decision about this mission is made. And now the mission is almost finished, almost home. One final stretch remains. There is no runway. No concrete strip of ground where a capsule can touch down gently and roll to a stop. No airport, no highway. Just the Pacific Ocean, stretching in every direction, flat and deep and indifferent to the fact that 4 human beings are about to slam into it at 17 miles per hour. Splashdown is not a gentle landing, it is an impact. The capsule hits the water surface, and the deceleration is immediate, a hard stop that the crew feels in every part of their body. The water does not give the way you might expect. At that speed, hitting water is closer to hitting concrete than it is to sinking into a pool. The capsule was built for this. The bottom of the hull is designed to absorb the shock. The crew is strapped in. They have trained for the impact. They know what it feels like because they have practiced it in water tanks and simulators dozens of times. And then, silence. The capsule bobs. It floats. The engines are gone. The parachutes are gone. The fire is gone. The radiation, the blackout, the speed, the heat, all of it is behind them now. For the first time in 10 days, the spacecraft is simply sitting still, rocking gently on the surface of the ocean, and the 4 people inside it are alive. This is confirmed. Splashdown in water rather than on land is a deliberate choice, and it goes back to the earliest days of American spaceflight. Water landings are safer for high-speed returns because water absorbs energy more uniformly than solid ground. A landing on concrete or soil at the wrong angle could be catastrophic. Water forgives mistakes in ways that hard surfaces do not. The recovery operation begins almost immediately. A Navy ship, positioned nearby and waiting, moves toward the capsule. The crew of that ship has been practicing for this moment for months. They know exactly how to approach, exactly how to secure the capsule, exactly how to bring it aboard without damaging it or putting anyone at risk. On Artemis I, the recovery ship was the USS Portland. It took roughly 2 hours for the team to complete all of the initial procedures in open water before the capsule was brought aboard. Imaging, testing, securing, every step documented, every moment recorded. Medical teams are waiting on the ship. The moment the capsule is secured and the hatch is opened, doctors are ready. The crew has been in microgravity for 10 days. Their bodies have changed. Their muscles are weaker. Their balance is off. They may need help standing. They may feel disoriented in ways that are difficult to describe to someone who has never experienced it. But they are alive. They are home. The 48-hour window has closed. The capsule will be towed to port. Engineers will examine every inch of the heat shield. Every piece of data collected during the flight will be studied for years. But all of that comes later. Right now, the mission has done the one thing it absolutely had to do. It brought them back, and what that means for the future of everything, that is the last thing we need to talk about. 4 people left Earth. 4 people came back. That sentence is simple. What it represents is not simple at all. For the first time in over 50 years, human beings traveled beyond the edge of the world that made them. They crossed a boundary that most of us will never cross. They flew past the point where every signal from home disappeared. They looked at a landscape that almost no one in history has ever seen with their own eyes. And they came back alive, carrying data that will shape how our species moves through the universe for generations to come. Artemis II was not a landing. It was not the moment humans set foot on the moon again. That is coming. That is Artemis III, and it is being planned right now, built on everything this mission proved. But Artemis II was something arguably more important than a landing. It was a proof of concept. It was the mission that answered the question every engineer, every scientist, and every person who has ever looked up at the sky and wondered has been asking for decades. Can we actually do this? Can we take human beings beyond the bubble of protection that Earth gives us, keep them alive, and bring them home? The answer, if the mission succeeds, is yes, confirmed. The data collected during this flight is enormous. The radiation readings from beyond Earth's magnetic field, the performance of the life support system under real conditions with real people inside it, the heat shield data from 2 separate atmospheric entries at lunar return speed, the biological data from 4 crew members who lived in microgravity for 10 days while scientists on the ground studied them continuously. All of that data feeds into the next mission, and the one after that. Artemis III will attempt what has not been attempted since 1972, a crewed landing on the surface of the moon. It will use everything learned on Artemis II to get there safely. The trajectory, the reentry profile, the life support, the heat shield, all of it refined, all of it improved, all of it informed by what 4 people experienced on this flight. And after the moon, Mars. That is the destination that has been hanging over everything from the very beginning, a trip that could take 6 months each way. A journey that will require solving problems in radiation protection, life support, and crew psychology that Artemis II has only begun to address. But begun is the word. The door is open now. It was not open 53 years ago. It is open today. The 4 people who flew this mission did something that cannot be taken back or undone. They proved that the path exists. They proved that the engineering can work. They proved that human beings can leave, survive, and return. That is what Artemis II is. It is not just a flight. It is not just a test. It is a statement, a declaration made not with words, but with the simple, undeniable fact of 4 people coming home from somewhere no one has been in half a century. The clock that started ticking 48 hours ago has stopped. The next one is already being wound.